Assalamu alaikum dear students. In today's lecture we are not going to start any new topic and we are not going to learn new methods. We are just trying to solve few questions from chapter 6, particularly from 6.2 and 6.5 article. So let's start. Here is question number 1, which is from exercise 6.2, and this is question number 9 of the exercise. Now in this question, what is minimum number of students, each of whom comes from one of the 50 states, okay, who must be enrolled in a university to guarantee that there are at least 100 who come from the same state. So in this case, our students are pigeons and pigeonholes are 50. Okay, so we have to find this n such that n over 50 ceiling function is greater or equal to 100. All right, and now if this answer is 99, then the ceiling function will be equal to 99. So we just need the answer of this term, that is n over 50, must be greater than 99. So the only possibility to make it greater than 99 is the 99 multiplied by 50 plus 1. Okay, so this is the integer which is greater than which for which n over 50 is greater than or equal to 100. So at least we must have 4961 students to make sure that at least 100 are coming from the same state, okay, when there are 50 states, right? So this is actually the application of generalized pigeonhole here. Okay, question number 15 from same exercise, exercise 6.2. How many numbers must be selected from the set 1, 2, 3, 4, 5, 6 to guarantee that at least one pair of these numbers add up to 7? Now, let's find out the pairs which add up to 7 from these numbers. They are 1, 6, 2, 5 and 3, 4. And there is no other pair which can add up into 7. So we must include one of the pairs. So if we choose two numbers from this, that two numbers can be 1, 2. So we are not able to find a pair which add up to 7. Again, if we choose three numbers, 1, 2, it can be 1, 2, 3. We are choosing randomly, so they can we can come up with 1, 2, 3. So even then we cannot find a pair in which add up to 7. So let's choose four numbers from this set: 1, 2, 3, 4. So now we have a pair 3, 4 which add up to 7. So we have to select at least four numbers to have at least one pair of these numbers which add up to 7. Okay, question number 19 from same exercise, exercise number 6.2. Suppose that every student in a discrete mathematics class of 25 students is a freshman, a sophomore, or a junior. Okay, suppose that every student in a discrete mathematics class of 25 students is either a freshman or a sophomore or a junior. So part A is show that there are at least 9 freshmen, at least 9 sophomores, or at least 9 juniors. It means that one of the group must have the 9 members. Either it is a group of freshmen, it is a group of sophomores, it is a group of juniors. Okay, let's assume otherwise, that this is not the case, and no group has 9 members. Every group can have at most 8 students. Okay, so if every group can have at most 8 students, then total number of students will be at most 24, but our students are 25. So this is a contradiction, and so the statement is true that at least one of these groups must contain 9 students. Okay, part B, we are going to solve again by contradiction. show that there are either at least 3 freshmen, at least 19 sophomores, or at least 5 juniors in the class. Well, again, we assume that this is not the case, and there are at most 2 freshmen, at most 18 sophomores, and at most 4 juniors, and this makes a total of 24 students. Again a contradiction, because we have 25 students, so this statement is true. Okay, question number 23. It's a bit tricky question. Show that whenever 25 girls and 25 boys are seated around a circular table, there is always a person, both of whose neighbors are boys. Okay, when 50 persons are seated around a circular table, and let's assume the seats are numbered from 1 to 50. So there are odd numbered seats are 25. Similarly, even numbered seats are also 25. And keep this in mind, first seat is adjacent to seat 50, so all the seats are adjacent to each other. So let's assume that no more than 12 boys occupied the odd numbered seats. Then at least 13 boys occupy even numbered seats. Okay, if maximum number of boys who occupied 12 who occupied odd number seats are 12, then of course rest are seated on the even number of seats, so or vice versa. So let's assume that at least 13 boys occupy the 25 odd number seats. Okay, 13 boys occupy the odd number seats. Then 2 of those boys must be consecutive in order, because total odd number seats are 25, and 13 boys are occupying odd numbered seats. Okay, so then 2 of those boys must be consecutive in odd numbered seats, and the person sitting those 2 boys always have boys as right and left neighbor. Consecutive odd number seat means one of the boys is seated on 1 and the other on 3, right? So we don't want this. But if 13 boys are occupying odd number seats, then this is going to happen. So there is no way to not being the case. Okay, so that is how. So if this happens, this will happen, of course, and the person sitting between those two boys, the person sitting between those two boys, I forgot to write between. So the person sitting between those two boys always have boys as right and left neighbor. Okay, and of course the person sitting between those two boys uh, will be seated on an even number seats. Okay. All right, question number 39. So this is left for you, because there is a hint. You can do it with the help of example 9. This is similar to example 9. So try it. If you are not able to do it, let me know. Then I'll try and solve for you. Okay, next is the exercise 6.5 and question number 7. How many ways are there to select 3 unordered elements from a set with 5 elements with repetition is allowed? So 3 unordered elements. We have to pick 3 objects from 5 types, right? From a set of 5 elements. All right. So we have with repetition allowed. So we have to solve this type of equation, and this allows us to solve by using this formula, repeated combinations. 5 plus 3 minus 1, that is n is 5, r is 3. So 5 plus 3 minus 1, c 3, and answer is 35. Question number 21. How many ways are there to distribute 6 indistinguishable balls into 9 distinguishable bins? Now in this case we are going to use theorem number 2 of your book, and this is again for repeated combinations. In this case n is 9, and we have to choose 6 distinguishable balls. So R is 6. So 9 plus 6 minus 1, C 6. And this gives us 3003, the answer. Question number 20. How many solutions are there to the inequality x1 plus x2 plus x3 is less or equal to 11? Where x1, x2, x3 are non-negative integers. So hint is given here. Introduce an auxiliary variable x4. So if x1 plus x2 plus x3 is less or equal to 11, so we have to add some number to make it 11, and that number is, which I forgot to write, x4 is also greater or equal to 0. If this is equal to 0, then sum is equal to 11 because of this, because there is equality here. And if x4 is greater than 0, then this is greater than 11. So x4 is greater or equal to 0. This is very important to write. Okay, rest you know how to solve it. This is repeated combination problem. So R here is 11 and here is 4, because 4 types, we have to choose 11 objects from 4 types of objects. So 11 plus 4 minus 1, C 11, and we have the answer 364. Okay. Question number 31 from exercise 6.5. How many different strings can be made from the letters A, B, R, A, C, A, D, A, B, R, A, using all the letters? Alright. So this is the application of theorem number 3, and in which formula given is that the number of ways can be found by this formula: n factorial divided by n1 factorial, n sub 2 factorial, n sub 3 factorial, n sub k factorial, right? So this is the formula we are going to use. So in this case n1 is 11, because count all these alphabets: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so n is 11. Now n1, count A's: 1, 2, 3, 4, 5. So there are 5 A's. n1 is 5. Okay, then B, 1, B2. So there are 2 B's. Okay, and 2 is 2. And then R, 1, R2. So N5 is 2. N3 C, C is 1. N4 D is 1. And 5 plus 2 is 7, 8, 9, 10, 11. So we are done with all the letters. So sum of all these ni's must be equal to n. So answer is how many different strings. So the number of strings is equal to 11 factorial divided by 5 factorial, 2 factorial, 1 factorial, 1 factorial, 2 factorial, which is 83160. So that is all for today, and now you can solve the questions from exercises of chapter 6. Keep practicing, and if you find some difficulty, do let me know. So practice is the key. Practice makes a man and a girl as well perfect. Okay, good luck. Thank you. Bye bye.